like the introduction because it certainly is a crazy idea. But as we've gotten into it, it's gotten more and more exciting for a number of reasons. When this all first occurred, I had been to a SSI session in Princeton, and at that particular point in time, the popular subject was lunar mining. And it kind of occurred to me as I was coming home on the airplane that if they're going to talk about all the traditional materials, mining the moon for iron and bauxite and all the other good things that we normally use, that we might as well get into the act with some composite materials. And so initially, SSI did some very modest funding, and we started looking at whether this was really feasible or not. And we looked at all the materials that came back from the Apollo missions, and sure enough, no problem, apparently, as far as what was available on the lunar surface to convert to composite materials, particularly, of course, the fibers. The lunar regolith is just scattered with free glass, for example, because of the eons of meteor impact on the lunar surface melted down these regolith materials and formed them into glass nodules that are everywhere. And so what we were really looking for as we got into the thing was, can we really do this from regolith materials? Do we have to go out there and find a specific ore vein or a specific kind of material in order to produce these fibers? And what we were hoping for, of course, is that we didn't have to do that, that we could essentially take a dustpan and sweep it up and dump it in the vat, and we could get the fiber out the other end. And the deeper we got into this thing, why, the more it began to look as though, yeah, maybe you really can do that. And but we went ahead then, and from the terrestrial base, we looked at the standard formulations for making glass fibers and looked at what was available up there if we really did separate these materials, and found that everything that we use here on Earth is available up there, and so sure you can make fibers that exactly correspond with the fibers that we're making here. But then we started looking at things like just taking basalt rock and melt that down and see if it will make reasonable fibers, and sure enough it does. And that's what began to excite us then, was the fact that maybe you can have a pure old crude approach to getting back there and establishing that initial lunar colony. You don't have to do something super sophisticated. You can take what we began to call the mud hut approach, where you just take these relatively crude materials and you build a relatively crude habitat. One, of course, that's safe for life maintenance and so on, but nonetheless crude. Problem was, though, the fiber, the reinforcing fiber, was straightforward and easy, but the matrix was a different problem, because here on Earth, everything we've ever known about composites revolved around the fact that we used an organic material as a matrix. Of course, on the lunar surface, there aren't any organics. Haven't flown across the pole yet, but as far as we know, there aren't any lunar organics. And so what are we going to do about that? Well, again, looking at terrestrial technology, for years here on Earth we have used frit-type materials, or low temperature glasses, for doing things like painting your refrigerator, for example. Porcelain enamels are in use every day in your household appliances and so on. So we started again looking at the Apollo materials to see if in fact we could do that. A little bit of a problem because there aren't any volatiles up there. And here on Earth we use volatile type elements in order to reduce the melt temperatures of glass. But with a little looking around, we discovered that we could indeed put together a glass from lunar regolith materials which would melt in somewhere around the 850, 900 degree range Fahrenheit. And by great coincidence, right at that point in time, here on Earth, we started fooling around with thermoplastic matrix materials in the airframe industry, and it happens that they melt in about the same 850 to 900 degree range. So we got a lot of free research going on here in terms of how do you do this and with what methods and so on. And so anyway, that was the basis of getting us really rolling on this thing. And as we began to roll, then we began to see some other things about this possibility. And that is that the problem with normal, traditional materials is that pure aluminum isn't really much good for anything in terms of structures, nor is pig iron really much good for anything. And that's true of most of the traditional materials. And so if you really are serious about using lunar resources to build with and or export with traditional materials, you're talking about doing things like first hauling out of the deep well here on Earth all of the mining equipment first to go find that ore, dig it out, and then the smelting equipment to reduce it down to those original forms. And then because even in the original form it isn't too great, then you're talking about alloying equipment to bring it around to the point where it really has some structural integrity. And boy, you're talking about hauling a lot of tonnage up there to try to do that kind of conversion. And so then we began to really kind of get excited about this thing, because what it began to look like is as though we might be able to convert this material, initially at least, in a very crude form, but structurally sound enough and handleable enough so that we could in fact build a mud hut approach type of initial colony. And of course, once you can get that established, then you can start refining all of these processes. And when you get to the point where you want to start exporting it, which of course is the whole reason for doing this in the first place, you can continue to refine and refine until you have something that's a really sophisticated kind of a material. So about the time we got to that point, we'd just been kind of putting in our own time and a little bit of SSI's money. And then McDonnell Douglas heard a paper or so that we gave in this subject, and they began to realize that this may really have some impact. And so we put together a triumvirate of three companies, McDonnell Douglas, Space Studies Institute, and Alcoa goes with the engineering. And now we began to really get serious about this thing. I'm going to really quickly run through this stuff. This is probably a slide that you've seen 314 times so far in this time. But threw it in there just to introduce the fact that we are now also apparently on the leading edge of starting to really do some space construction. And so this whole idea of getting to revisiting the moon and then being able to export materials from the moon for space construction begins to really have some significance. And as I said a minute ago, of course, the initial approach was, let's get at that by lunar mining. And then we kicked in the composites thing, and there have been a lot of studies, as a matter of fact, on making glass fibers in particular from lunar materials. And this slide that's up here now is one of the concepts of how a lunar glass fiber operation might look. And this is what we're actually working with now. McDonnell Douglas has these two parabolic reflectors, or concentrators I should say, at their plant in Huntington Beach. These concentrators were built back during the energy crisis and have sort of been gathering dust ever since. And so we're putting them to some good use now. And for those of you who are not familiar with the glass fiber making process, by and large what it amounts to is taking a crucible of some kind or a furnace of some kind, putting a multiple hole bushing in the bottom of it, heating up the glass to the molten point and letting it flow through those multiple holes, and then picking up those individual fibers in a bundle and wrapping them on a wind-up drum and regulating the speed of that wind-up drum to give you the fiber or the filament diameter that you want to produce. And this is a typical glass fiber bushing in operation. You can see the fiber strands coming off of it, and usually this is a platinum rhodium alloy bushing. This is just a slide to give you an idea of what the standard formulae are in terms of glass making. And as I said earlier, all of these things are available in abundance in the regolith. And then this is a typical formula for making the low temperature glass matrix material, or low melt temperature glass matrix material. And this is the popular science version of our little project. They recently published an article, and their group put together this lunar glass facility. And of course, what we'd like to really achieve in all of this is that we'd like to be able to hook right into whatever method is finally adopted for taking oxygen from the lunar materials. And we'd like to just hook right into that line. If it's a heat reduction line, which it probably will be, we'd like to be able to just hook in and use the slag from that operation to take it right on into the fiber. By doing that, we could achieve all kinds of economies, particularly economies of hauling up the original equipment to do it with. And can't quite see that from here, but I think it's one of our, a fellow named Charlie Coggan, one of our associates working with the high temperature press that we developed in order to combine these materials into sheet form so that we could get some physical properties. And as I said earlier, what you want to wind up with ultimately is some kind of initial lunar colony that is a mud hut type of approach. And of course what you're ultimately wanting to do, and Greg earlier referred to the Boeing baseline approach, and this incidentally was artwork from the original Boeing baseline approach back in the mid-70s or late 70s. And so that's what you're ultimately after, is to export those materials out to construction sites of this nature. And again, this is the SPS program that was put together like that. And at that time, back in the late 70s, we were approached by NASA to put together a beam building machine to go into the cargo bay of the shuttle, erect itself in low Earth orbit and spew out a continuous length of triangular truss beam, as you see in this slide. The idea being that to put together the SPS platform, that you would, the shuttle would run out these continuous lengths to some finite length, and then cut it, tether it, run out the next beam, and so on, and then reorient ultimately, as shown in this diagram, reorient to 90 degrees to the original beam direction, run out the cross members for the beam, tie them together, and now you have the basic structure for your SPS platform. And this is the initial prototype machine that we built to accomplish that task. And this is a hunk of the triangular truss beam that we built with that initial prototype machine. Greg said everybody's got to get with this if anything's going to happen. And there's a very interesting story about this. We did this in the late 70s and it disappeared. We hadn't heard anything about it until about 5 months ago, I guess, and this was an absolutely astounding coincidence that I came into work one day and there was a letter in my in-basket saying that was from the gentleman who runs the Space Cadet program at Huntsville. And in this letter he said, we ran you down through your logo, and he said, when I take my kids on these tours through the facility here at Huntsville, he said, the thing that seems to fascinate them all is that hunk of beam that's in the lobby there, because even the tiniest one of these kids can go over and pick it up. And then he wound up by saying, what the hell did you build that thing for anyway? So it happened that afternoon I went to a composites conference, and a fellow from NASA Ames got up and gave a big erudite paper on how NASA was now engaged in developing a beam building machine. That afternoon I came home and there was another letter in my in-basket. It was from the French Atomic Energy Commission. And they were saying in their letter, could you please get us a copy of your final report on that beam building contract you had with NASA? And this astounded me so much that all these three things would happen in one day after this thing having disappeared for 15 years.
It was probably their kids. The kids saw it in space camp. They reported back to their parents.
Probably. So anyway, I sat down and wrote a letter to Fletcher and said, what the hell's going on here? And I got a letter back, not from Fletcher, but from one of his lieutenants, a 5. And I pointed out to him that now that we're getting into space station, that the space station we've designed is a series of beams and modules. So it looked like this kind of technology might be useful again. And I got this polite letter back so that they had other priorities. At any rate, this beam building technique, I think, is a very valid technique, and there are a lot of ways to approach it. The original beam builder that you saw on the previous slides was one where
we'll take a couple of questions and then have the rest of you pour out in the back. Yes?
I didn't pick up where you stand as to the mixing of the fibers and the low melting temperature glass. I saw the bit about the press, but you didn't go into anything further.
I did that deliberately. The toughest part of this thing is going to be to take these two allegedly useful materials, the matrix and the fiber, and combine them into some useful form or some useful structural shape. And that's a sort of a separate problem from the one of actually producing the two materials in the beginning. But that's why we're doing this press work, was to get some feel for how much, whether we could do these at 0 pressures, we could combine these materials and form them at 0 pressures, or whether we're going to have relatively high pressures. And of course, all that dictates what kind of equipment you'd have to use to even form them up crudely in the beginning.
Right.
For your work on the lunar surface, as far as feedstock is concerned, would you be better off in any way if you had a deposit of pure glass of uniform composition, several meters deep, on the lunar surface, and were to use that material as your raw material as opposed to starting messing around with those glass and regolith of the lunar soil?
Yeah, maybe. It isn't really that well defined as to whether that would be beneficial. We looked at the fact that there's all this free glass that is actual pure glass.
The glass in the lunar regolith is not really pure. It's contaminated with little fragments, little blebs of iron. And
sure.
Yeah.
Sure. What I really meant is that it's already melted glass. And then there may not even be any benefit from taking that already melted glass. But you're for sure right that if we could separate it and bring it into a pure formula like I had on the screen there, the kind of formulae that we're using on Earth, it would be a obviously better controlled process than just sweeping it up and melting whatever you're looking at.
Thank you very much for a very interesting talk.